Alright, just a little review from what we did yesterday, some practice questions. So what we're doing here is finding the length of the arc. So remember, the length of the arc is the portion of the circumference. So I'm just going to kind of highlight the arc. Now, they tell us this is 90 degrees. So the measure of my arc here is actually going to be 270 there. So they're giving us the 90 so we can figure out the measure of our arc. So I just did 360 minus 90 to get that. Okay, now length of your arc, you got measure of the arc over 360. That's the percentage of the circumference that you want. And we're going to multiply that by 2 pi times the radius. And if you guys remember from what we did in our previous lesson, if I want to leave this in terms of pi, I'm just going to type all the numbers in. So 270 divided by 360 times 2 times 8, and then we'll just write a pi next to that. So I didn't include the pi, so I'm just going to include that at the end. And then arc length is like a perimeter or part of a circumference, so it's just going to be the units. It's not squared. All right, this guy here gives us the measure of the arc by giving us the measure of that central angle. So 150 out of the total 360, I want 150 degrees. And this one says the nearest tenth. So the only difference I'm going to do here is I'm going to go ahead and type everything into the calculator. So 150 divided by 360, that's the percentage. If you want to hit equals and look at that, we want about 42% of the circumference. And then when I multiply that by the circumference to hit my pi button, and then we're going to multiply that by 19, and all simplified be 49.7-ish to the nearest tenth, so I better put approximately equal to. And so this is my about 42% of my circumference to get that arc length. All right, and then sector area is similar, except we're talking about an area here. So I want the area of the shaded part in terms of pi. Now, they're giving us the central angle going all the way around here is 315. So to get the measure of the arc we're looking at, I'm going to do 360 minus 315. So this is just going to be 45-degree central angle, which will match the measure of that arc. So it's the measure of your arc over 360. That's the percentage of the area I want this time, times my area formula, pi r squared. Okay, now when I do this guy, here's what we're going to do. 45 divided by 360. I'm not going to multiply it by pi. I'm going to multiply it by the 8 squared, or you could type in 64. That's going to be 8. And then we'll just put a pi next to that. And this is going to be centimeters squared here because we're talking about an area. Nearest tenth. If this is 105, I'm going to do 360 minus 105. That'll be the central angle for the arc we want to find here, 255. So our measure of our arc going this way is 255. So out of the whole area, I want 255 degrees out of the 360. Pi times my radius, which is 14 there, squared. Now for this one, nearest tenth is going to type everything in. 255 divided by 360, and then times my pi button, and then times my 14 squared. And so this is going to be about 436.2, and this will be yards squared. Okay, now for what we are going to work on today, which is finding the area of a segment of a circle, it's going to involve finding the area of a triangle as part of the process. So what I have here, you guys are used to finding the area of a triangle 1/2 base times height. I'm going to show you an alternative way to find the area of a triangle here real quick and just kind of explain through and then do a couple examples, and I'll try and go through this, but this will be a much faster way to find the triangles, and I'll explain that on the back with what we're going to do today. Okay, so just starting out here, I'm going to go through this triangle. So find the area of a triangle 1/2 base times height. You guys already know that, and I've got some labels in this picture here. So the base would just be B, this just segment right here. The height is this h. Okay, what's going to go on in this little proof is I'm going to show you a way to find the height here if you don't know it. So here's the height, and you'll notice when you drop the height that creates a little right triangle. And so the triangle I'm really focusing on right now is just going to be here. Now, if you just look at that triangle, we're going to bring back some little trig skills. The height is opposite angle C, and the base is not included because it kind of cuts off right here, but the other side that is included in this triangle is the A, and that's actually the hypotenuse because of where it's positioned from the right angle. So I would say to you here, the sine of angle C is equal to the opposite over the hypotenuse. So it would be the height of the triangle over that side A. That's all they've written right here. And then what's going on in this problem, I'm just going to get the height by itself real quick. And to do that, we would multiply both sides by A. So you're going to see this over here, but the height would be A times the sine of C. Okay, so I call this the side angle side area theorem. It's not technically called that, it's just to help me remember. But what they're going to do is they're going to substitute this in for the height in the area formula, and you guys will see it like this. So if you know an angle, and this is between the base and this side here, so that's why I call it side angle side. So if you know these two sides and the angle between, you can use this little formula, the setup with the sine, to figure this out. So it's 1/2 the side, both of those measurements, times the sine of the angle between the sides, and that will work to give you the area. All you're doing is substituting that little trig in for the height. So let me come down here and explain this to you guys. So I'll do one where I'm going to actually drop a height here. So I know these two sides, 26 and 34, and I know this angle, 54. So let me just put an H for the height there. If I wanted to find the height there, what I would do, this 54, the height would be the opposite, the 34, I don't know why I started to rewrite 34, would be adjacent. So opposite, oh my gosh, sorry guys, opposite hypotenuse. Opposite hypotenuse is sine. So I could say the sine of 54 is the height over the 34. If I want the height, it'd be 34 times the sine of 54. If I want the area of the triangle, 1/2 the base, which is 26, times the height, which is what we just solved for, the other side times the sine of the angle there that we know. And I'm just going to check the mode on my calculator real quick to make sure it's in degrees. But then to do the area, it's going to ask you to round to the nearest tenth. So I'm just going to type this right in. 1/2 times 26 times 34 times sine of 54. And so this is pretty big here. Let's say approximately equal, since we're going to round, 357.6, and this would be inches squared. Okay. So you don't have to, but if you want to, what you're trying to do when you do this process for finding the area is drop a height so that one of the sides is definitely going to be one of the sides in the little right triangle. I could do that right there. What's going to happen here though, if you just remember what I did with that process, if you want to just use that 1/2, it's the two sides, 15. These are both 15 in this case. And then we would do sine of 46. If you want to go through the process and think about, okay, this is the opposite, this is the hypotenuse, so sine 46 is your height over 15, multiply both sides by 15, and then think about this when you're plugging in for base times height. You can do that, or if you want to kind of just remember the process, as long as you understand it, it's 1/2 the side, both sides multiplied together, and then it's always the sine of the angle between, because this is always going to be opposite the angle, and then the 15 is always the hypotenuse. So if you want to set it up, or if you want to just remember kind of how it goes, that's fine too. That formula is also on your formula sheet under the area formulas. And for this particular example, I'm going to say approximately equal to, since we're rounding, 80.9, and this would be meters squared. We're talking about area. Okay, now I paused my video to write down this definition, so you guys feel free to do that too. But what we're going to focus on today is finding the area of what we call a segment of a circle. And so I've got a little picture there, and one of the parts of the definition we actually have not gotten to yet, so I kind of did two definitions in one here, but we will talk about what a chord is and a lot of properties of chords here as we go through this unit. But for the moment, I'll just go through the definition here with you. So here's the segment of a circle. You can see it's shaded, it's an area, it's a region, so the shaded area here, bounded by what we call a chord. And I'm just going to kind of highlight the chord here real quick. A chord is just a line segment where the endpoints are on the circle. So just a little line segment. It's not part of the area. The chord would just be the line segment. And then the segment itself of the circle is bounded by the line segment and then the circle's circumference. So that shaded area between that line segment and then the circumference of the circle, that's called a segment. Now, the process for finding the area of that is going to involve what you know about finding the area of a sector, and then what we just looked at, that triangle formula I gave you, will make this really quick to do. So let me kind of draw in just like a little, like eyeball the center. I'm just going to draw in a little dotted line. So if that triangle right there was filled in and we had a central angle there, we would be finding the area of a sector. So that's going to go with the concept. So you can see here, they're going to kind of fill in what I outlined right there. They're going to say, okay, that's the sector. The triangle part, which is kind of hollow over here where I started this out, we don't want that part of it. The leftover would be the segment. So the concept behind this, find the area of the sector, subtract out that triangular part, and then you'll be left over with the segment. Okay, so this is not terrible to do, because what you're going to have every time is you're going to need to know the central angle measure, so 60. B to C is a radius, but B to A is also a radius. So I have two sides. So in terms of that triangle there, I can just use that formula we used on the front. And then you guys hopefully will remember the area of the sector from what we did in our previous lesson. So the sector there, if everything was filled in, what we would do would be the measure of our arc, which is 60 over 360 times pi times our radius squared. Okay, so let me simplify that just a tiny bit, and I'm going to write it on the line. So ultimately we're going to round this to the nearest 10. So let me do 60 divided by 360, and I'm going to multiply that by 4 squared. I'll try and leave it in terms of pi. Now when I did that, you guys can see I got kind of a nasty number. So let me just show you a little trick. If you have a graphing calculator, if you hit the math button, and that very first thing will say FRAC for fraction, just hit enter twice and it'll convert it into a fraction. So that's 8 over 3. So here's how I would do this, 8 pi over 3. Now let me grab a scientific. So you can do that on a scientific. I'll show you exactly how. Most of you guys have a similar calculator. I'm going to do 60 over 360 times that 4 squared. And again, I'm getting that long decimal. On these calculators, let me scooch this up a little bit so it's on the screen. If you hit second and then this F to D, it'll convert it from a decimal to a fraction. Okay, now right here, this is a mixed number. So this is 2 2/3. Let me just show you right underneath that button. This one will change it from a mixed number to an improper fraction. So I'm just going to do one more thing. I'm just going to hit second, this ABC key, and then that'll give you that 8/3. So that's a quick way to simplify that using the calculator. Okay, now area of the triangle. Here's what I'm going to do. If you guys think about, I'm just going to, if I drop a height here, if you want to think about, it's going to be opposite hypotenuse. So the height of that is going to be the sine of 60, but we'd multiply it by 4. So area of the triangle, 1/2, the base would be 4, and then the height would be 4 times the sine of 60. So I'm going to leave this as close as possible, so I'm not rounding till the end of the problem. So I'm going to do 1/2 times 4 times 4. So we'd have 8 times the sine of 60 for the area of the triangle. Now what I'm going to do from the segment, I'm going to take the sector, which is this, and I'm going to subtract the area of that triangle, which is going to be simplified to that. Okay, so in my calculator, 8 pi over 3 is the sector, and then we're going to subtract, so I'm going to put this in parentheses, 8 times the sine of 60. Alright, so whichever calculator you want to grab, let me do it on the scientific because you guys, a lot of you have this one. Okay, so I'm just going to do 8 and then hit my pi button, divide by 3. And then I'm going to subtract, and then here's where I got to put parentheses, 8 times the sine of 60. So I'm going to make sure I put that in parentheses so I subtract that triangle. And then we're just going to round this to the nearest tenth, it says in the directions. So this says 144, so I should round that to 1.4. I know that 9 there would round that up, but we're not going all the way down the line. So this would be 1.4, and this is an area, so it'd be centimeters squared. We'll try this one more time. Okay, so to find the area of this segment, again, I'm going to find the area of the whole sector. Pretend that triangle is shaded in there. So it'd be 90 over 360 pi times my radius squared. So let me go ahead and I'm just going to use this one because it shows up on the screen a little bit better, but 90 divided by 360 times my pi button times 6 squared. Oh, crud, I'm going to leave it exact. Let me do that again real quick. I'm not going to put the pi in there. There we go. Now, that ends up being a nice number. So this is just going to be 9 pi. So that's the whole sector if everything was shaded in there. Now, the triangle. Again, this is a 90-degree angle. It tells me that under the directions. These two sides are both the same. So area of this triangle, 1/2, you can do the side times the sine of the angle between them. So it'll be sine of 90. So let me simplify that real quick. We're just going to do 1/2 times 6 times 6. So it'd be 18 times the sine of 90. Okay, so area of the segment then, I'm going to do 9 pi minus, this is the sector, so I'm going to subtract the triangle. I would put this in parentheses. And the leftover has to be that little segment that's shaded in there. Sorry about the beep from the phone. Okay, so again, here, let me grab this so you guys can see it on this calculator. Alright, so I'm doing 9 pi, and then minus, just put this in parentheses, 18 times sine of 90. And so my area of the segment here to the nearest tenth, I'm going to say about 10.3, and this guy was inches squared.